Yes. So in the last part, we saw about how upstream Mach number and downstream Mach numbers are related in normal shock wave. So in this part, so we are going to extend our ideas, what we discussed so far, to get the properties such as density, pressure, and temperature across the shock wave, normal shock wave. Right? Okay. So we arrived at a 1D momentum equation, that is rho 1 u1 is equal to rho 2 u2, or I can write rho 2 by rho 1 is equal to u1 by u2. So if I multiply and divide it by u1 to this equation, so what happens? I get u1 square divided by u1 u2. So we got one condition while solving the energy equation, that is u1 times u2 is equal to a star square. So I am going to use that condition over here. So if I use that one, what happens? Rho 2 by rho 1, which is also equal to u1 by u2, equal to u1 square divided by a star square, or this is nothing but m star square, right? So I have a relation for m star. So this is, sorry, m star 1, right? So u1 by a star. So that is m star 1. So I have a relation between m star and m. So if I use that one, so that gives me rho 2 by rho 1 equal to u1 by u2, which is also equal to m1 star square, that is gamma plus 1 times m1 square divided by 2 plus gamma minus 1 m1 square. Right. So this is the property change. So that is density change across the normal shock wave, or which also relates the velocity change. And you see here, this is rho 2 by rho 1, this is u1 by u2, because in the downstream the velocity is going to decrease, whereas density is going to increase. So if I keep m1 is equal to 1, I get rho 2 by rho 1 equal to 1. So there is no change in density. If I keep m greater than 1, then I get rho 2 by rho 1 also greater than 1. So the condition is this density change goes exponentially and reaches infinity when upstream Mach number becomes infinity? That one we have to address now. So if I have to address that one, so again, if I keep limit m tends to infinity, I get rho 2 by rho 1 tending to gamma plus 1 divided by gamma minus 1. So it goes to a finite value. For here, that is gamma is equal to 1.4, I get rho 2 by rho 1 tending to 6 for for m1 tending to infinity. Right. So this is a density change across the shock wave. So similarly, we can get a pressure change. So that is from momentum equation, I have rho 1 p1 plus rho 1 u1 square is equal to p2 plus rho 2 u2 square. So if I use this one, so write in terms of p2 minus p1 is equal to rho 1 u1 times u1. I'm writing splitting that one, that is rho 2 u2 times u2. So rho 1 u1 is equal to rho 2 u2 from the momentum. So that gives me, if I take rho 1 u1 common, that gives me u1 minus u2. And this is p2 minus p1. So if I divide the entire equation by p1, so that gives me p2 minus p1 divided by p1 is equal to, here I am taking u1 common, so that becomes u1 square divided by p1 is equal to 1 minus u2 by u1. Fine. So again, from the speed of sound, we formulated that a square by gamma is equal to p by rho. So I can use here, if I use that condition, what I get? I get this is P2 by P1 minus P1 by P1 is 1 is equal to U1 square divided by A1 square times gamma times 1 minus U2 by U1. So what is U1 square by A1 square? That is nothing but Mach number. So that is M1 square times gamma 1 minus what is U2 by U1? We saw that is also equal to rho 1 by rho 2. That is nothing but 2 plus gamma minus 1 times M1 square divided by gamma plus 1 times M1 square. So keep P2 by P1 one side like this is equal to 1 plus gamma M1 square times, if I take the LCM, so that becomes gamma plus 1 times M1 square minus 2 minus gamma minus 1 times M1 square whole divided by gamma plus 1 times M1 square. So now we can see this and this can be cancelled. So that leaves me that P2 by P1 is equal to 1 plus gamma by gamma plus 1 times. This is if I take M1 square common, that is gamma plus 1 minus gamma plus 1 minus 2, right? So I can take this gamma get cancels. This leaves me 1 plus 1, that is 2 M1 square minus 2, right? So my P2 by P1 relation now looks like 1 plus gamma this M1 square already cancelled, gamma divided by gamma plus 1 times 2 M1 square minus 2, right? So that is nothing but P2 by P1 is equal to 1 plus, if I take 2 common, 2 gamma divided by gamma plus 1 times M1 square minus 1. So this is the relation between the pressure change across the normal shock wave, and this is also a function of upstream Mach number alone for a given calorically perfect gas, right? Again, this from this equation you can see, if I keep M1 greater than 1, that is supersonic, so that means P2 by P1 is also greater than 1 for M1 greater than 1. P2 by P1 is equal to 1 for M1 is equal to 1. And in this case, as M1 tends to infinity, P2 by P1 also tends to infinity. That means the pressure change across the normal shock wave is not bounded. So it can go to any value as M1 goes to higher and higher. So this is very important. So as a designer, so when we have to design a supersonic or hypersonic materials, I have to take care if I am going at a higher speeds, that means my pressure load on the object's surface will be higher as um, directed by the nature, because across the shock wave the pressure change is not limited. So if I increase the upstream Mach number, I'm going to see a higher pressure on the downstream side. So this is important, right? So now how we can calculate the temperature change? So we are going to get the help of the equation of state, because we already saw that to solve 5 unknowns, we need a 5 equation. So that one of the equations we considered is equation of state. Now we are getting that help. So that means I have T2 by T1. So if I use P is equal to rho RT, so that means P2 is equal to rho RT2, rho 2 RT2, and P1 is equal to rho 1 RT1. So if I just divide one equation to other one, so I get T2 by T1 is equal to P2 by rho 2 times rho 1 by P1. So that is something but P2 by P1 times rho 1 by rho 2. And we already know that one, P2 by P1 we calculated. So, and rho 1 by rho 2, that means rho 2 by rho 1 also we know. So that gives me 1 plus 2 gamma divided by gamma plus 1 times m1 square minus 1 times 2 plus gamma minus 1 times m1 square divided by gamma plus 1 times m1 square. So this is again T2 by T1 as a function of Mach number. Again, T2 by T1 is greater than 1 for M1 greater than 1. T2 by T1 equal to 1 for M1 equal to 1. And again, T2 by T1 tends to infinity as M1 tends to infinity, because T2 by T1 is going to infinity. So again, we see here the temperature change across the normal shock wave is not bounded. So it is not going to reach a limit value. Rather, it shoots up to infinity as M1 tends to higher and higher values. So this is also an important consideration. So now we saw all the properties across the normal shock wave. Similarly, we can also write the property change across the normal shock wave as a function of as total properties. Like I have the total temperature, total pressure, and all. So, but energy equation, whatever we used, H1 plus U1 square by 2 also equal to H2 plus H2 plus U2 square by 2, which is equal to H naught, which is equal to constant. This is for adiabatic flow. We saw that H naught total enthalpy remains constant. Even for a calorically perfect gas, T naught is constant. So that leads me T naught 2 is equal to T naught 1. So this is fine. The total temperature across the normal shock wave is not going to change as dictated by the energy equation, or it's an adiabatic flow process. So the total enthalpy and for calorically perfect gas, total temperature remains same across the shock wave. But what about a total pressure? Is it going to be same? No, because this is adiabatic but not a reversible. So it is an irreversible process. So it is not isentropic process. So what happens? I have S2 minus S1, that is equal to Cp ln of T2 by T1 minus R ln of P2 by P1. So I can express this in terms of total properties, that is S2 minus S1. This is nothing but S02 minus S01. But given that upstream and downstream of the shock wave, they are still isentropic. Only across the shock wave, we have an adiabatic change. So S2 minus S1 equal to Cp ln of T02 by T01 minus R ln of P02 by P01. So what happens now? Because T02 is equal to T01, so this becomes ln 1. So logarithm of 1 is going to be 0. So all I left with is S2 minus S1 is equal to minus R ln of P02 by P01, or I can write P02 by P01 is equal to exponential of minus S2 minus S1 divided by R. So there is an exponential decay or exponential loss of total pressure across the normal shock wave, because I can show that S2 minus S1 is also a function of M1. So as M1 increases, M1 tends to infinity, P02 by P01 also tends to lower values. So, and this is also important because we know the second law of thermodynamics governs me that S2 minus S1 has to be positive. That means delta S is increasing. The entropy has to increase. This also tells me one more important point, that I cannot have a normal shock wave when M1 is less than 1. So mathematically possible, mathematically, because those equations we derive are from energy, continuity and momentum. So they are not going to stop me saying if I have a subsonic Mach number in the upstream, so that gives me some value of M2 supersonic value the downstream. So from the governing equation point of view, but laws of thermodynamics is not allowing me to have those kind of solutions, because if M1 is less than 1, my M2 is greater than 1, but the delta S, the change in entropy will be negative in those scenarios. So that is not possible as governed by second law of thermodynamics. So that is why nature also doesn't have the solutions, or the normal shock wave scenario doesn't exist if there is a upstream Mach number that is subsonic. So we can encounter a normal shock waves only in the flows which is supersonic. So that is important, right? So now all these property change what we discussed so far can be put into a graph like this, right? You see, so M2 as a function of M1, so with decreases and reaches to some limit value, that is 0.378 something, right? It is going to reach that value as M1 tends to infinity. Similarly, the density change also tends to a limit value 6. And these two curves that corresponding to P2 by P1 and rho T2 by T1, they tends to infinity, or they are unbounded. So they are not going to reach in a limit. As M1 increases, the value of P2 also increases, T2 also increases. Whereas for a P02 by P01, so that is exponentially decreasing to some value, the limit value. Right. So this is a property change across the normal shock wave. And also, as I said earlier, if I have a normal shock wave, my S01 that is equal to S1 and S02 that is equal to S2, because we treat this is isentropic. The flow in the upstream is isentropic, flow in the downstream is isentropic, but across the shock wave that is adiabatic. This is what we are treated. So I can still use an isentropic relation, only the properties relating to downstream. So that means I can write P02 by P2 as a function of Mach number, like 1 plus gamma minus 1 by 2 times, but I am here using the downstream Mach number. I can use this isentropic relation. Similarly, I can use the upstream relation with upstream Mach number. So these relations I can use still only relating to upstream, downstream to downstream. When it comes to relating downstream and upstream, that is P02 by P01. So then I am using the normal shock wave relation, that is e to the power of minus S2 minus S1 divided by R. Similarly, when I have to relate P2 by P1, I am using this relation, what we derived for normal shock wave. Similarly, rho 2 by rho 1 is like this. So across the shock wave, I have to use the normal shock relation that is derived with adiabatic flow assumption, whereas only upstream properties or only downstream properties relating to the downstream properties alone, I can use the isentropic relation. That is fine. Okay. So now we will take up some of the questions which is asked in the previous year gate. So one is across the normal shock wave, which of this property, so which of this statement is correct? So option A says both total temperature and total pressure decreases. Option B says both total temperature and total pressure remains constant. The total pressure remains constant, but total temperature decreases. Total temperature remains constant, but total pressure decreases. So we already saw that T naught is constant across the normal shock wave. So the option 1A is not correct because it's saying both of them are decreasing. T naught is remaining constant. Again, this is not the case because total pressure is not constant. So we saw that P02 by P01 is equal to e to the power of minus S2 minus S1 divided by R. So we saw that it exponentially decreases. So it is not correct. So total pressure is not going to constant. So only option which is correct is option D, that says total temperature remains constant, but total pressure decreases. That is correct. And the next question, a student needs to find a velocity across stationary normal shock. He measures the density and pressure across the shock wave as shown in the figure below. The figure is not given, so I am going to give you the figure. So it is given, I have a shock wave which is sitting over here. So he measures the properties, that is P1 1 bar, P2 29 bar. Yes, rho 1 he measures, it is 1.2 kg per meter cube, whereas he measures the density downstream of the shock, that is 6 kg per meter cube, and U1, U2. So he has to calculate what is U1. So they are also given the conversion factor. 1 bar is equal to 10 to the power of 5 pascals. They are asking what is the value of U1, and they clearly mention no shock table is needed for the calculations. So that sense, we'll try to solve this one. So from the given information, so we derived that P2 by P1 across the normal shock wave is 1 time 1 plus 2 gamma by gamma plus 1 times M1 square minus 1. So from here, I know P2, I know P1. So 29 bar and 1 bar. So that gives me 29 minus 1 is equal to 2 gamma by gamma plus 1 times M1 square minus 1. Or if I take this one, that is 28 into gamma plus 1 divided by 2 gamma plus 1. If I take the square root, that is nothing but M1. So gamma is 1.4 for the air, and 2 ones are 2, 14. So 14 into 2.4 divided by 1.4 plus 1. So this gives me M1 is equal to 5. So now I have M1. So now I have to calculate what is U1. So that is what they are asking. So I know M1 is nothing but U1 by A1, or U1 is equal to M1 times A1. M1 we already calculated. So M1 times A1 can be written as gamma P1 by rho 1. So P1 known, rho 1 known. If I use all the information available to me, so I get U1 is equal to 1707.83. in meter per second. So they are asked to calculate in meter per second. So I am also getting the answer in meter per second. So this is 1707.83. Right. So similarly, there can be a different questions which can be framed out of normal shock wave ideas, and we can solve that by applying the proper relations, and assumptions should be correct, and we should also know how the relationship works across the shock wave and how these relations can be used only in the upstream part or only in the downstream part. So though if you are clear with that one, so we can answer any number of questions which is asked in asked from normal shock wave topic. Okay, so that ends my discussion on normal shock wave. So for more information, you guys can feel free to contact IIT Gate classes. And thank you for listening.